Drafts number 118. Sorry about the delay. It would not be Space Drafts, as I said earlier, without having a technical problem. But we have sorted things out, at least we have somewhat sorted things out, and we will kick this night off. So, for all of you who are new here, a very special welcome to all of you. This is Tucson's version of Astronomy on Tap, a network of events in bars and pubs spread throughout the world to bring astronomy to you, the general public. My name is Nick. I am a graduate student at the University of Arizona. And tonight we have a show for you consisting of one talk and then trivia, which we are very excited to be bringing to you tonight. During our talk tonight, there will also be an opportunity for you to win a little bit of our merch with one trivia question in that talk. So during that talk, when that trivia question comes up, please raise your hand, and we will, and you might be able to win a little piece of our merch. We will also have some little prizes for those who do the best at our space trivia in the second half of our show. Now, I did say merch. We do have merch available for sale over here at this table. We only are able to accept cash, unfortunately. So if you did not bring your cash tonight, please come back in September and bring your cash with you for a little piece of our merch. It's going quick, and some of it is legacy merch from a previous iteration of Space Drafts. Now, without further ado, let's begin tonight's first talk. Here to introduce us to the impacts of space weather, not only on outer space, but on our lives here on Earth, please give a warm welcome to Tyler Reese from the Lunar and Planetary Laboratory.
Howdy. So I'm going to talk about the who, what, when, where, and why, and how of space weather. I'm Tyler, and I guess we'll just talk. So who is space weather? We'll start with the easy questions. Who is space weather? Who? Yeah, any ideas? Me, I'm space weather. I'm Mr. Space Weather, so who am I? I'm Tyler. I'm a radiation effects engineer at Raytheon, so I've been doing that for a while. I'm also a PhD student at the Lunar and Planetary Lab. So what do? I think about space weather all day. I think about how it works, and then I try to make something out of it. So that's usually pretty important. So next question. What is space weather? Is it that? UFO crashes in New Orleans. Katrina brought it down. The government covered it up. The government is lying to you, but not about this. So this is not space weather. Space weather is in space, so it's that. Let's see. Well, it doesn't show up. Okay. It's space. It's the thing that's not Earth. So it's radiation in space. There's lots of types of radiation: neutrons, high energy photons, high energy electrons, ions. Lots of radiation, and it's in space, and can come from lots of places: the solar wind, the sun, galactic sources. And then when it's charged, it gets trapped in Earth's magnetosphere and does all kinds of fun things. So then we're going to skip around. Why is this important? Why are you stuck here listening to me today? Well, I think we should do the trivia first. Why is space weather important? Well, it costs money. So how much does it cost per year for a U.S. space asset? So let's see, we got one number. Oh, a second number. Ooh, this is fun. A third number. Oh my God. So yeah, what do we think? I got to give away free stuff that's not mine. I got one. You got your hand up.
C.
C. He says C. Oh, good job. $10 billion. Great job. Yeah. That's a lot of money, right? So, like, to contextualize that, right? That's a James Webb per year. The lifetime cost of James Webb is about $10 billion. And so we spend one of those every year trying to, protect things or put them back up after space weather takes them down. So that's pretty important to me. And of course, it's going to continue to be important. The space economy is growing. We're thinking it's about $1 trillion globally. In 2025, it grew 80%. So as the space economy grows, the need for space weather is going to grow, right? More and more stuff is out there that's impacted by space weather. And so that $10 billion is going to seem like nothing soon. Talk about inflation, right? So we're going to be reliant on space systems, so we're impacted by space weather. And so here's my favorite example. This is the easy example. In 1989, there was I think it was an S4 I'm looking at Robert, my friend. Was it an S4? He says yes. Yeah, so it was like an S4 class, solar storm, knocked out the Quebec power grid. If that happened today in like a random U.S. city, they're thinking that that's like 40 million people affected. That's a huge economic impact, maybe like $3 trillion. That was the 2015 estimate, so maybe higher now. But that's a big deal, right? So, I'm trying to do it in my head. That was a long time ago, but now it's even more important. And then, I think this is very academic focused, so we don't care about useful things like power grids. We care about future research. How does this impact future research? I see Artemis, Habitable Worlds Observatory. I've heard someone mention that. Laser interferometer there in space. LISA. What do all these things have in common? Yeah, they're in space. Yeah. It's future space mission, science research. Guess what? You have to radiation harden that. That stuff's affected by space weather, and you should care about that, right? So I think we've generally proven, I think, that space weather is important. So where is it? It's in space. I just told you. When is it? Now. So the solar wind, right? Space weather starts at the sun. There's a solar wind, and so it's hot, very hot, magnetized plasma coming off the solar atmosphere. A movie play? No, it doesn't. What a bummer. All right, there's no movie. Imagine, if you will, a stream of corpuscular radiation coming off of the solar corona, but there's a wind from the sun. It's a gusty wind, right? And so it can be very, very fast, like a gusty wind, right? Or it can be steady at like 400 kilometers a second, right? And this is a solar system-wide phenomenon, right? The sun is everything. It's 99% of the mass and all of the fun parts, the solar wind. So again, when you see the solar system, it's all around with the solar wind. There's a magnetic field. It's in a spiral pattern, and you can see that on the graph on the bottom. And you can see Pluto way far out there, and there's still all this solar wind in between it and the sun and beyond it. And as it changes from fast to slow, that changes the configuration of planetary magnetic fields and all this good stuff. And so this is a dominant force in the solar system. And so when we say it starts at the sun, we're talking about the solar wind, right? And then how does the solar wind change? It goes with the solar cycle, right? So the peak solar activity, we call that solar max. That's when the sunspot numbers are high. There's peak X-ray flux, irradiance, and things like that. And so what's happening is the sun has a differential rotation, and as it rotates, its magnetic field poles flip, right? And as it's flipping, that's when it reaches solar max. So when it's like mid-flip, right? That's solar max, and then it repeats. So every 22 years, the magnetic poles switch sides. So every 11 years, you oscillate between solar max and solar min. And solar max is associated with solar storms. Oh no, that sounds scary. So a solar storm, right? Like I said, peak occurrence during solar max, just really emphasizing that same thing. It's a transient disturbance in the solar wind. It propagates outward from the sun, right? And it hits Earth. And you can see I got a power grid, I got a rocket ship. What do I got? What is that? That looks like a pipeline to me. I got satellites, no missiles, and I got Mars. So yeah, but it's everywhere, right? And it hits everything, right? And so where do solar storms come from? They're associated mostly with coronal mass ejections and solar flares. So coronal mass ejections are what really drive it. With these huge eruptions from the sun of mass, a coronal mass ejection, if you will. And they're very fast, and they're usually coincident with solar flares. And so we associate one with the particle flux, and we associate the other with the X-ray flux and radio blackouts. And so they're coincident phenomena, but both drive solar storms. And then what else do we have? What are they going to do? They're going to hit the magnetosphere. They're going to hit Earth at some point, right? And so Earth has a permanent radiation belt from the solar wind. And then when the solar storm hits it, it fills it up, right? And so you saturate it full of energetic particles, and now it's a huge hazard. It's a permanent hazard, and solar storms make it a bigger hazard, right? And then what else do we have? We have the other side of this. So we talked about solar max. Now we go to solar min. We have cosmic rays. So what a cosmic ray is an energetic particle. It originates from galactic origins, some kind of shock, supernova, something fun, and then it hits Earth, right? And it impacts Earth, it gets trapped in the magnetic field. And so what happens is, it really depends on the solar wind. That's kind of the non-intuitive part. So when it's slow solar wind, solar men, the heliosphere is sucked in, so there's more cosmic rays, there's less filtering. And when it's solar max, they're filtered out really efficiently. So you kind of always have a problem. You can't just say, oh, it's not solar max, I don't care. Well, you can be at a quiet time sun and you still have all these cosmic rays to deal with. So it pretty much always sucks to be in space. So beyond Earth, well, there's no magnetic field, so it's no problem. Wrong. No magnetic field, no problem. Right? That's dead astronauts, right? You're in the bare solar wind, you have no help. Right? And so the moon, right, it orbits the Earth, I just found that out. So sometimes it's in the Earth's magnetosphere, sometimes it's kind of magnetically shielded, if you will. And then other times it's in the bare solar wind. And so when it's in the bare solar wind, its dose is like 50 times that of what it would be on like a typical low Earth orbit satellite. And so that's kind of a big problem. You want to use the moon as a launching pad to Mars. Mars has the same problem. So something to think about. And then Jupiter's fun. So Jupiter's a lot bigger than Earth. Has a big, strong magnetic field, and because of that, it's saturated with very high energy electrons. And so traveling through Jupiter's radiation belt is different than Earth's because it's like trying to survive a nuclear bomb. That's the only other object that I can think of that would make similar radiation. And it's very, very large. And so we have an image here. If you could see Jupiter's radiation belt, it would look like this pink thing. Right? And so it's very large, it's very energetic, and it's a big problem. And so those are like kind of, the quick overview of what it might be. And so what did we learn? What have we learned? What have you learned? Somebody. Yeah. Space weather is important. I agree. It's variable. It's complex, right? But do we know how to live with it? So how do we live with space weather? You radiation harden stuff, right? Space ground systems. You have to figure out how to harden them. And then you got to fund scientific research because you got to predict this. We have no way to predict this. Like I can call the Hurricane Center. I can say, hey, is a hurricane going to hit Tucson? And they say, no, we live in Tucson. But we can't predict space weather. We rely on early warning systems. So IMAP is the newest puppy in the den, right? It's got eye alert. It's a new space weather alert system. GOES is a common one as well. But we have no way to predict it. We have early warning systems only, and so that's insufficient. So write your congressman, keep me employed. The end. All right, I'll do questions.
Your questions? Yes.
So how now would we deal with something like Carrington or something really big that?
Pray. We don't have a way to deal with it. That would be, that's permanent damage to the power grid. Yeah.
Do I hear a question? I have a
Question?
Yeah. We'll pick one.
Tyler, what is a vector?
What is a vector? It's the thing that acts like a vector.
I have a question.
Okay.
Radiation hardening. I've heard this term a lot. I'm not exactly sure what it actually means in terms of space assets. What does it actually mean when it comes to like a telescope or something?
Radiation hardness is the description of a system that is resilient to radiation effects. That's the definition that's on my resume. So it's you pick rad-hard electronics, which are electronics that are resilient to certain types of radiation with different types of effects. It's your concept of operations. How do you fly? And find, am I on the moon or am I on Jupiter? What type of radiation, what type of operation am I running? And so it's like an onion. All right. And so you have your concept of operations. Do you have shielding? What kind of parts do you use? And then you have to do firmware, software, design mitigations. So it's about how much do we get paid? $50 an hour? It's about that much for the problem.
Like, how often does Carrington event happen?
It's 1 in 10,000 years.
Oh.
Yeah, so I'm not sweating it,
Doesn't that like blow circuit breakers? And then kind of
Yeah.
doesn't cause major problems?
No, so the Carrington event was an extreme solar storm. It's notable because it was Carrington, I don't know, John Carrington, I don't know his first name. He saw it with his own eyes. He saw the solar flare, right? And so it would be a very large solar storm event. And so solar storms bring energetic particles. They bring all kinds of stuff. They compress the magnetic field. And so that compression of the magnetic field drives those currents that blow your circuit breakers. But that flux of high energy particles can start taking out satellites and things like that. And there's worse things than losing GPS. You might lose whatever.
What was the 89 one?
The 89 one, it was like a S4, S3, kind of rode the middle.
You know what carries each one?
Like an S5, about 1 in 10,000.
Is that like order of magnitude each one?
No, it's not. It's just, I don't know. They tried to match the hurricane scale. I take that for
That's
Noah.
logarithm.
So he says it's a logarithm, but he's wrong.
Which is 1 in 10.
I saw a question in the back.
Right. So, can you see solar weather moving, like small flares and
Yeah.
that maybe, because once the big flares, once you observe the big flare, it's too late. But can you predict those at all?
Yeah, right. So once again, I have to dispel the solar flare myth. Solar flares don't cause solar storms; they're coincident. But watching sunspots and seeing solar flares and stuff through our early warning systems, such as IMAP, GOES, several others, is what we do now. So we can't predict. We don't know when one's going to happen, but it's an early warning system. So, oh, I see stuff. I see activity in the sunspot. I see an increase. Okay, like everybody get on alert. Yes, I agree.
Let's do one last question.
So is the reason that we can't predict because we don't understand the physics of like how the sun is actually producing solar weather, or that we just don't have the sensing capability to fully sense the entire solar system?
I think it's both, but a lot of it is we don't know what the solar interior is like and stuff. We just know it's a lot of magnetic field loops.
With that, one more round of applause for Tyler. And with that, we will go to intermission. Right now it is, what is it, 8:50 or 7:55? So we will come back at 8:15. Don't forget your bartender, and we'll see you in about 20 minutes. And come get some merch if you want some.
I like a short, like 10 minutes.
Yeah, it's something a large.
I like to do like half